A transformer is an application of mutual inductance. It's an electrical component which can step up or step down voltage and current. And they turn out to be very useful in all kinds of devices, in all kinds of applications, ranging from device chargers to the electrical power grid. Transformers have the rule that V2 over V1 equals N2 over N1. One of the most important formulas involved is that the voltage of a coil is proportional to the number of turns in that coil. Shown here are two coils wrapped around an iron core. The iron core allows the magnetic field created by one coil to easily flow through the other coil. So the magnetic flux created by one of the coils will also be felt by the other coil. But the more turns a coil has, the more that voltage gets magnified. Now we can see that example A is connected to an AC source, and example B is connected to DC. As we showed in the past, both of these situations have the possibility of creating a voltage in the secondary coil. The direct current example has to have a magnetic field that flows this way, though, according to the right-hand rule, and it can only flow that way. This turns out to be a problem for transformers, because transformers need a changing magnetic flux in order for a voltage to be continuously generated in the secondary coil. So, with that in mind, after the current has been flowing through the primary coil for a long time, the induced EMF in this secondary coil of the DC transformer would become constantly zero. This means that it will not continuously operate after the battery has been connected for a long time. The secondary coil would only really respond if the battery were suddenly connected or disconnected from the circuit. For setup A, after the source has been operating for a long time, current through the resistor will be constantly changing direction. We showed that here when we showed that the source voltage had a nice sinusoidal shape, and then the voltage induced in the second coil would also have a sinusoidal shape. So interestingly, connecting just one of these coils to the AC source generates an AC voltage in the secondary coil. However, in example B here, after current has been flowing in the primary coil for a long time, the current through the resistor will be zero. Shown below is a transformer setup of two coils wrapped around an iron core. The iron core has a high magnetic permeability, so we can assume that the coils share approximately the same magnetic flux. Let's say that a cell phone charger is going to be plugged into household 120 volts AC, but it needs an output of only 6 volts AC to charge the phone. The transformer has 1500 primary windings, and it wants to step down the voltage. How many turns does the secondary coil need to have for this to happen? So we have a formula above for this. V2 over V1 equals N2 over N1. Just says that the number of turns in each coil will be proportional to the voltage of that coil. So let's say that the primary coil has voltage V1 and the secondary coil needs voltage V2. V1 is 120, whereas V2 needs to be 6. We also see that, according to the problem, the number of turns in the primary is 1500. We need to find out what is the number of turns in the secondary? So let's plug in. "75 turns."